Beneath the seemingly calm surface, two massive bodies of water are locked in a constant battle, creating underwater currents so powerful they can snap anchor chains designed to withstand hurricane forces. What we're observing is a complex hydraulic system unlike anything else on Earth, explains Dr. Maria Fernandez, lead oceanographer at the Mediterranean Marine Research Institute. She stands on the deck of the research vessel Poseidon, carefully lowering an array of current profilers into the choppy waters. These instruments will give us real-time measurements of what's happening beneath the surface, where the real battle is taking place. The Gibraltar Strait serves as the only significant connection between the Mediterranean Sea and the Atlantic Ocean. Through this narrow opening, a massive water exchange occurs daily that shapes the climate and marine ecosystems of both bodies of water. Most people understand that water flows through here, but the scale is difficult to comprehend, Dr. Fernandez continues, pointing to the monitoring equipment's real-time display. We're measuring approximately 30,000 cubic kilometers of water exchange annually. That's equivalent to nearly 8 million Olympic swimming pools worth of water moving through this channel every single day. The volume creates engineering challenges through its speed and direction. As the equipment's data appears on screen, Dr. Fernandez points to the readings with concern. We're recording current velocities exceeding 3 meters per second at certain depths, faster than an Olympic swimmer and strong enough to move boulders along the seabed. These currents create complex patterns, including powerful eddies and vortices that can extend hundreds of meters below the surface. The interaction between fresh Atlantic water flowing eastward on the surface and the saltier, denser Mediterranean water flowing westward underneath creates a layered system with extreme turbulence at the boundary layers. We've documented what we call internal waves within the strait, Dr. Fernandez explains. These are massive underwater wave formations that can reach 100 meters in height but remain invisible from the surface. When these internal waves crash against underwater structures, they generate forces comparable to storm surges hitting coastal buildings. Any bridge or tunnel crossing the strait would need to contend with these relentless forces throughout its operational lifetime. Marine engineers have calculated that the lateral force exerted by these currents could reach up to 50 tons per square meter on large support structures, equivalent to the thrust of a jet engine continuously pushing against each column. Dr. Carlos Alvarez, structural engineer specializing in marine infrastructure, reviews the simulations with visible concern. These forces fluctuate with tides, weather systems, and seasonal changes. This creates a particularly dangerous situation we call vortex shedding, where alternating pressures can set up resonant vibrations in bridge supports. This phenomenon has led to catastrophic failures before, albeit on a smaller scale. The famous Tacoma Narrows Bridge collapse of 1940 occurred when wind created resonant vibrations, and the forces at work in the Gibraltar Strait are orders of magnitude greater and more complex. Look at what happens to our model here. Alvarez points to a simulation showing a standard bridge support column. Even with our most robust designs, we see material fatigue developing within just years, not decades. The constant stress cycling from these currents creates microscopic cracks that propagate through even the strongest materials. Back on the Poseidon, Dr. Fernandez retrieves the advanced current profilers after their 72-hour deployment. The comprehensive data reveals another troubling aspect of the Strait's hydraulic behavior. We've identified rogue currents, unpredictable, extremely powerful flow anomalies that can appear without warning, she explains. These are similar to rogue waves on the ocean surface, but occur underwater where they're invisible until they strike. The engineering solutions required would be unprecedented. Traditional bridge supports would need massive reinforcement, dramatically increasing costs. Tunnel designs would need to account for these forces acting on entrance structures and ventilation systems. The Golden Gate Bridge deals with strong tidal currents peaking at around 2.5 meters per second, Dr. Alvarez notes. The Akoshi Kaikyo Bridge in Japan faces similar challenges, but the Gibraltar currents are faster, more variable, and occur at much greater depths. We simply don't have established engineering precedents for these conditions. The currents create another problem: scouring. The powerful water movement continuously erodes sediment around fixed structures, potentially undermining foundations over time. Engineers would need specialized protection systems to maintain structural integrity. We've documented scour holes forming around existing underwater structures in the strait that can reach 15 meters deep within just a decade, Dr. Fernandez explains. Any crossing would require constant monitoring and maintenance to prevent progressive foundation weakening. The financial implications are staggering. Engineers estimate that addressing the current forces alone would add billions to the already astronomical project cost. Specialized materials, hydrodynamic designs, and reinforcement systems would all be necessary. Dr. Alvarez gestures to the financial projections. We're looking at a maintenance cost multiplier of 5x compared to bridges in more favorable environments. That's before considering the extreme depth challenges we've already discussed. Some innovative concepts have emerged, including a submerged floating tunnel anchored at a depth where currents are less severe. This would avoid supports reaching the seabed, but introduces its own challenges, including how to secure such a structure against lateral movement. The truth is, we're still developing the engineering tools to fully understand how structures would behave in this environment over decades, Dr. Alvarez admits. Current simulation models have limitations when dealing with such extreme conditions. These hydraulic forces represent just one challenge in a maritime environment that has challenged navigators for centuries, creating conditions that will test both engineering solutions and the courage of those who would connect two continents.